Alright guys, should we get started? Alright guys, welcome to the UTMIST Reinforcement Learning Workshop Week 2. My name's Jessica, I'm one of the academic directors, and I'll be leading this workshop today. I guess just getting right into it, this week we're going to be looking at a little bit more of like dynamic programming, so like iterative methods, policy improvement, policy evaluation and all that. And we're also going to be doing a little bit of introduction to Monte Carlo methods. And if you're not already on our Discord or following any of our social medias, the link is on the screens, or the QR code to our link tree is on the screen where you can access everything. So if no one's on there, I'll give you guys like a second to get that. All right. So we'll go over a little bit of we'll go over a little bit of week 1 review first of all. So if you were here last week, great. If you weren't, well, I'm just going to quickly go over some of the material. So the first things first, you're at a reinforcement learning workshop, and well, the goal of reinforcement learning, it's pretty much, it's very different from like supervised learning or unsupervised, because the main thing is that you have an agent, you have an actor that is interacting with an environment. So you're not categorizing things, you're not putting labels, you're actively like interacting, and you're achieving a goal. This goal usually is to maximize your expected return, which is kind of at the end of a trajectory, at the end of the episode, the total reward that you're able to get. So that's what is represented by G. One second. Yeah, the next thing that we kind of introduced was KRM bandits. So this kind of introduces the idea of what an agent is kind of like, so interacting with an environment. So basically the setting is you have many, let's say you have like 3 different baskets, and you're picking numbers from each basket. You want to get the pie, and each basket has like a different distribution of these numbers. You don't know what it is, and you want to try to figure out how can I get the highest reward at the end of, let's say, picking 100 numbers. And how you do that is using sample averages. You don't know what the numbers in the baskets are, but you can estimate them just by using the experience that you have gained. And then we introduced the idea of epsilon greedy, or exploration versus exploitation. So the whole idea of this is basically you want to exploit, which means you are just using your current knowledge to get the highest short-term reward possible. But you also want to explore, which is more so like getting a better sense of your environment so that you can maybe benefit more from it in the future. And there is this idea of like epsilon greedy action selections. So this wasn't very clear last week. I'll just make it a little bit more clear. So when we say epsilon, you can think of that as how often you're exploring. So it's kind of like the probability of exploring. This is what's on the screen right now is kind of usually how epsilon greedy is done. So the bottom one right there, the uniform, that's your exploration. Your top one, argmax, that's just you picking the best action possible at this time. Oh yeah, question?
Does the exploration also include the most optimal one that they have?
So your uniform is like over all of your actions. So like you could pick a different one. You could just so happen to pick your optimal action. Yeah, so it's pretty much fair games for everything. Next was the idea of Markov decision processes. So it's basically you start in a state, take an action, get a reward, go to the next state, and it's this like continuous trajectory of experience. And the main property of this is that if you're an agent, you're choosing your next action. The only thing you need to rely on is the current state that you're in. So it doesn't matter if you were in like state 1 or state 2 in the past. All that matters right now is that you are in state 3, and that's all you need to determine your next action. Yeah, so the next thing that we went over is kind of what an RL agent consists of. So there are like 3 main things. Model we're not going to talk about because it's a little bit like detached from everything else that we're doing. But essentially you can just think of it as like the model is the agent's just imagining the world by itself. The other 2 main things that we focused on are policy, which is how the agent's behavior functions, so how it's choosing its actions, and the value function. And specifically in Markov decision processes and MDPs, this is an agent's belief of how good each state or each state action pair is. So it's kind of like how good of a spot am I in right now, or like in this state. So continuing with value functions, this is typically how you define how good a state is or how good a state action is. So it is the expected return. Sorry, let me restate that. Assuming you're following a policy pi, your value for state S is the expected return, assuming that you start in state S and follow policy pi onwards. And then for a state action value, it's pretty much the same thing, but you're in state S and then you take action A. So they're related, but they're a little bit different. The main thing is that state action value is that you just have an extra action that you're taking. And then this was a little bit rushed at the end, so I'll go a little bit more into it. There are like various different types of RL agents. You have value-based, policy-based, and actor-critic, which is kind of like a mix of both. Value-based, so every single RL agent will have a policy that no matter like if you're value-based or policy-based, the main differing factor is how you are learning this policy. So in value-based RL agents, the agent is learning the value function to generate the optimal policy. But if you're, let's say, in policy-based, you're learning the policy directly. So this could be through policy gradient, which is what PPO. So like I forgot what it stands for. I should know this, but it's like it's kind of like it's a variant of gradient descent and such, where you're learning the policy directly. Was there a question? Yes, proximal policy optimization. Thank you. All right. Before we go on, are there any questions? Yep.
Is policy similar to like an algorithm that allows you to choose the best action?
Yeah. So you can think of it as kind of like if you're assuming we're still in MDP, so like finite states. If you're in a state, your policy will basically, it could be a distribution of like which action you want to take next. So let's say if you have like a uniform policy, there's equal probability of choosing all actions. Or if you just have like a deterministic policy, it could just be, if I'm in this state, I'm taking this action no matter what. Yeah. Yeah, so think of it as a probability distribution.
It's like something again like chess, like value-based. Because the policy, the values are kind of like.
It depends on the algorithm. It's not really dependent on the environment. It's dependent on the algorithm.
Oh,
if that makes sense. Yeah. All right. So we're going to assume no more questions. We're going to go into a little bit of dynamic programming and Bellman equations. So first things first. Dynamic programming, the entire idea is that you're breaking down a complex problem into smaller sub-problems. And then once you solve these sub-problems, you can just put all the information together to solve your big problem. And why we are doing this is because, well, if you're doing reinforcement learning, you might not want to recalculate every single value, every single number that is already calculated. So you just use the ones that you already have pre-calculated to create your new estimate, to create your new value. Yeah, so an example of dynamic programming, if you're unfamiliar, it could be like the Fibonacci sequence, where you're using the previous two numbers to calculate the next number. So if you wanted to calculate, like, say, the fourth number in the Fibonacci sequence, you would need the previous two, you need the second one, and you need the third one. But then to calculate the third one, you need the first and second. So you can kind of like build it up from there. So you have the sequence of 1, 1, 2, 3, 5. Yeah, so this is like a really basic example of dynamic programming. And if you, like, I'm not sure about the engineering course one, but like, if you want to learn more about this, CSC 373 algorithms. Yeah. And then next we have Bellman equations. So Bellman equations are, they're the basic building block to solve MDPs. They're recursion, it uses recursion to help you find the optimal policy and value functions. So remember how I said like you're using your previously computed actions or previously computed values to calculate your new value. That's where the recursion comes in. And the main question that it's answering is what is the maximum reward an agent can receive, assuming they take optimal action, assuming they take the optimal action now in this stage that you're currently in, and for all future actions. So so this week we want to find an optimal policy. We're trying to find the best policy so that the agent can get the best reward at the end. Yep.
So for this one, are we considering like discount factor to be like 0?
That discount factor is...
Because you said like optimal action now, right? So we're trying to optimize it.
We'll get into that a little bit later. But that is like a design choice. It's a hyperparameter which you can tune to see how well your your agent will perform. Yeah. Oh yeah, and then hyperparameters are just kind of like values that it's something that you can we call that you can tune so that you're able to like hopefully find a better policy, hopefully find a better agent. And an example of a hyperparameter actually is epsilon. You can choose how much you want to explore. Yeah, so we're going to go into the Bellman equations for these for the state value function. So if you recall, we first have our value function, which is just your expected return, starting if you're in state S. This is assuming you're following a specific policy pi. And you can expand this. So this is kind of where your recursion comes in. If you expand the summation in the corner over here, you get GT plus 1 out. And so that's your future rewards for your future states. And your RT plus 1, that's the reward that you're going to be getting next. And this gamma term right here, that's your discount. So to review, your gamma is how much you want to consider future rewards, or how important you want future rewards to be in your calculations. And this GT plus 1 is actually, you can actually just rewrite it as your next state, the value of your next state. And now, because of how expected values work, you can write all of these as summations over probability distributions. So first things first, if you're in a state, you're able to choose an action. So that's first why we're iterating over actions. And then remember, policy is like how you choose your action. So this is like the probability of choosing action A if you're in state S. Next, after you choose an action, you go to a next state, and then you also get a reward. So that's what S prime and R is. That's your next state and your reward. This transition right here, so P, S prime, R given SA, that's your environment transition. So this is the probability of seeing the state S prime and your reward R, assuming that you started in S and you took action A. And this R plus gamma of your value is just this right here. It's just your next, it's just the reward and your next value. So this diagram might make it a little bit more clear of what's happening. So we're first starting in a state. From there, you go to you choose your actions, so that's the black dots, and then from your actions, you go to a next state, and you also get a reward. So this is kind of like what's happening in like the summations and the double summations and such. Oh yeah, if I'm ever going too fast or have any questions, yeah, feel free to stop. Yeah, is this clear to everyone? All right. Yeah, so we can actually do the exact same thing with state actions, state action value, and then, yeah, so we can find the Bellman equations for these. Bellman equations, again, is like recursion. You're using your previously computed values to determine your new value. So we can expand this once again. Something to note is that because we're already given an action, we don't need to iterate over actions anymore. So we immediately, we're in a state, we take an action, we end up in the next state, and you get a reward. So that's why we're, if you recall from over here, that's why we're missing this policy, this summation over your actions. Yeah, and then once you've taken this action and you're in the next state, you're assuming that you're taking the optimal value, or you're taking the optimal action going forwards as well. So you also want to consider your states. That's why we have this, instead of just you queue function immediately, it's this expectation of over states. And just out of curiosity, does anyone think that this looks familiar? Does it look familiar to something? Yep.
S.
Yeah.
But instead it's T plus 1.
Yeah. So you can when you're going to a next state, you can think of the you always have to take the value of a state somehow. So in here we're just your value function is just another way of writing it. But here, since we're not using the value functions, this is what it's written as. And then this might look a little bit scary, but we're just expanding it once more. If you recall from our this state value function, we iterate over all of the possible actions starting from that state. So that's kind of what's happening here now. We're taking a next action as well. And then we can actually simplify this to just be Q. Yeah, this might look a little bit confusing as well, but again, this diagram will probably make it a little bit more clear of your trajectory. So instead of starting at a state for your state action value equation, you start with an action, and then you take this action, go to a next state, and then from here, you then expand over all your actions. So that's what this summation over here is doing with this policy. All right. Are there any questions? Yep.
Go back to the tree.
Yep.
What is this smaller case Q type?
So sometimes we use lowercase, sometimes we use uppercase, but these are like uppercase Q, lowercase q, these are all your state action value equations, yeah. 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 I already gave you guys kind of a preview to this page, but yeah, so it's just looking at the equations themselves, it's a little bit confusing, but so let's actually just walk through an example. So let's assume that you want to recompute your state value equation, state value for this red state over here. So these assume that these circles are states, and the numbers inside them are the current values, the state values for those. And the square over here is a terminating state. So like once you reach here, you can't get out. Yeah, and then each arrow is an action or a different path that you can take. And let's just assume that we have a uniform random policy. So if we're in this state right here, we have two actions that we can take. We can be a good student and study, so we have a 50% chance of doing that. Or you can also, if you just took a midterm, go to the pub and drink your sorrows away. And that's the second action that you can take. So using this Bellman equation right here, let's just start walking through it. So first things first, let's say I just bombed a midterm, so I want to go to the pub, but unfortunately only 50% chance of that happening. So that's what we're starting with. Your policy is a uniform random policy. So yeah, that's where the 0.5 comes from. And then the next thing is your probability of your transition function right here. So these, let's say that these numbers are your probabilities of going down these paths. Yeah, so let's do the first one right here. You have a probability of going to this negative 1.3 state of 0.2. And for all the rewards here, no matter which state you end up in, you just get a reward of 1. So for your first value, we're going to do 1, which is a reward. I'm not going to do 1 multiplied by everything, because once you add it up at the end, your reward is just going to equal back to 1. And then you have 0.2 times negative 1.3. So that's assuming you went in this direction, that's the probability of ending up in this state, which has a value of negative 1.3. All right, is that clear? Yep.
Where did the 1 come from?
The 1 is your reward. So the reason why I just, it's a little bit unclear, but it'll like make sense once everything is written out. Your reward, you do multiply by your probability, but then because everything added up is just 1, we're just going to straight up write the reward as 1 for now, just to make it easier to see after. Yeah, so that's one state. And then let's say we go this path. Can someone tell me what the numbers are that we're multiplying for that path? Yep.
0.4 times 2.7.
Yep. So that's 0.4. Oh, shoot, go away. Okay, whatever. 0.4 is your probability of ending up there, and 2.7 is your current state value for that state for your next state that you're ending up in. And then this last arrow. Oh my gosh, sorry. Yeah, this last arrow. It's a little bit blocked right now. But it's also like 0.4 chance of going back to your original state. So that's where this number is coming from. And like I said earlier, because all the rewards, they add up to 1, if you were to expand it out, it would be 0.2 plus 0.4 plus 0.4. So that's where the 1 comes from. All right, so we finished this side, and now the other side. All we have to do, well, there's only one path that you can go. There's only one next state that you can go. And yeah, so it's just 0.5, which is your probability of taking this action. And because we're in a terminating state, your reward is just 0. So, or not your reward, your next state value is just 0. So if you add all of these up, it's 7.4. You get the same value. So this can mean this could possibly mean that your value function is now stable. It's converged to a point. Yeah, let's do a thought experiment now. let's say I'm in this state, negative 2.3 at the top, and I want to maximize my future reward. So, assuming that you have full autonomy over which path you take, or which action you do, which action should I pick if I'm in this state? Should I look at Facebook again, or should I quit? Quit.
Look at TikTok.
Okay, I don't think that looking at TikTok is an option here, but quit is the correct answer. And why is that?
Okay.
Yeah, well, or if anyone, yeah, let's go with you. Why
We're
is
gonna
that?
go to a better state
Yeah.
with a higher value. Like we're
Yeah.
gonna improve by one at least.
Yeah, so so the next state that we end up in has a higher state value. And just to reiterate, state value is your expected return at the end of an episode. So if you go to this state right here, the state value, the expected return is better than what you started with. All right. So going from this state now, what would you want to do? Study, yeah. And why is that again? Yeah, yeah, perfect. So we're going from 1.3 to 2.7, which is like a much better expected return. And one thing to note is that even though it looks worse because our immediate reward is -2 compared to an immediate reward of -1, it's the fact that we're considering all future rewards as well. So therefore, immediately this action might look worse, but in the longer term, it looks better. Yeah, and from here, I think it's same thing if you're in this next state actually. So the best action or the more optimal action to take would be to study instead of sleep, even though you get a lower immediate reward. Yeah, question?
I have a question. So when we calculate the report, we use the values negative 1.3, right?
Yeah.
What do we do if we don't know these values in the first place? Because in order to get negative 1.3, and within the diagram, we also have to refer to the 7.4 state, right?
Mm-hmm.
So what should we do if we don't know the values of those states?
Yeah, you're getting a little bit ahead of the lecture actually. So what we're going to do is that assuming we have a policy, we can actually calculate our values for these states. So we'll be getting into that, but like you exactly have the right idea. This is what we're going to be covering this workshop. Yeah. Yeah.
How do we know if the immediate reward outweighs the expected value? Like, are there cases in which if it's good enough?
Yeah. So in this case, I guess I didn't make this clear enough. I forgot to say our gamma is 1, based on how calculations worked out. Our gamma is 1, which means that we're taking full consideration of the future rewards. So depending on how you evaluate your gamma, that's how like you're gonna choose your next actions and such. Yeah. All right. So we kind of alluded to of like which actions is better, which state is better, but then like that was just kind of just thought process. So let's actually formalize it a little bit. So first things first is optimal policies. So just to reiterate, policy is how an agent thinks. It's how it chooses its actions. And then assuming we're in a finite Markov decision process, if we have a policy pi, we'll consider that policy to be better than or equal to another policy pi prime if its expected return is greater than or equal to that of pi prime for all its states. This might seem like a lot of words, so I simplified it into a couple of if and only if statements, so for definitions. So if you go over all of your states, if the value for your policy pi is greater than the value for pi prime, that means that policy pi is better than pi prime. And then an optimal policy, which is denoted by a star, so pi star, is better than or equal to all other policies. And you can also have possibly more than one optimal. Yeah. So we're assuming, let's assume that the y-axis is your value and your x-axis is just a continual set of states. So like each tick is a state. So like each line would represent the value of one policy for each for a state. So looking at this graph, who thinks policy 1 is better than policy 2? Who thinks policy 2 is the better one? Who thinks it's none of them? You guys are correct. The last one, so policy 2 nor policy 1, they're not better than any of them because they have this overlap. There are some states where policy 1 is better, and there are some states where policy 2 is better. So you can't really confirm that one is better than the other because of it's not the same for all states. Now, if we look at this next graph, we can actually see here, we can see definitively that policy 1 is better than policy 2 because its value for all its states is higher. But then we have this policy pi star at the top that just, it's triumphing over everything. Its values for all of its states are better. So in this case, just looking at these three policies, pi star at the top would be the optimal policy. And this is how these policies are ranked. Is this clear? All right, perfect. Yeah.
Just wanted to ask, this is like an arbitrary things, like for the first graph. Why isn't policy 2 better than policy 1? Because we can see.
This is just an arbitrary example.
Oh, it's just arbitrary.
This is just an arbitrary thought example.
Okay.
Yeah. But like if we, I guess like in this case, why is it not better? It's because it's not consistently, the value isn't consistently greater in all the states.
Okay.
Yeah.
But if we had like actual values, then we could calculate which one is better, even if they intersect, right?
No, if they intersect, if they cross over, one of them is not better than the
Okay,
other.
there you
Yeah.
go.
So we can actually use these. Oh yeah.
Oh, sorry, there's a question in the chat.
Oh, question in the chat? Yeah, sorry, I just missed that. Is it guaranteed that we can find a policy that is greater than or equal to all other policies? We'll be getting onto that. But assuming that like you're in a finite situation, the quick answer is yes. So we have optimal policies. Now let's go to optimal value functions. Okay. So we kind of did a little bit of this earlier when we were choosing when we were going through that diagram of studying or going to sleep. So all optimal policies will share the same optimal state value function. And kind of what's happening here is that this is assuming that this is the expected value, assuming we're following the optimal policy. And how you can find that just simply is that if you go over all your policies, all of the possible policies, you just take the policy that maximizes your value for that state. And then we can do the same thing for your state action value functions as well. Yeah, so again, you're just going over all of your policies, and you're choosing the best policy that will give you, or you're choosing the policy that will give you the highest value. And based off these, we can now create a Bellman optimality equation for these optimal value functions. So let's start with the state value function. So recall this is what our Bellman equation was. This is our recursive Bellman equation for a state value function. And now let's assume that we're taking the optimal policy. So from here, remember how we were kind of choosing the best action or the best next state to go to? Really, all you're doing is that you're assuming you're picking the best. You're assuming you're picking the best action that will maximize your future states. So that's what this max A is doing here. This is you iterating all of your actions going from that state, and you're just picking the action that will give you the highest value. And yeah, that's your Bellman optimality equation for state value functions. Are there any questions? All right. And then again, we can do the same thing for our state action value functions as well. So here's our policy. Let's assume that we're taking the optimal policy. We're taking the optimal policy. And then we just need to pick the best action. We need to pick the value of the best action. So how we already did this a little bit earlier, but to a little bit formalize it, how would you pick the best action if you're in a state? So let's say the white dots are states and the black dots are actions that you can take. So let's say that you have these three, let's say that these three values are these summations computed for each action. In this case, which one would you take? Which action would you take? Yeah, the one in the middle. And that's because, well, it's the max. It gives you the highest value. So in this case, if you have your optimal, state value function, this is how you can find an optimal policy. So you're just taking the argmax. You're taking your policy is just take the best action. That will give you the highest value. Yeah. So let's do a walkthrough example of this actually. So we're trying to find the optimal policy in this grid world. And let's say gamma, your discount factor is going to be 0.9. So instead of 1 this time. Let's start with the blue state. And let's see what our value is going up. So if we choose to go up, the probability of going, let's just say that the probability of like going to each of these states is like you're always going to end up in the state that you in the direction that you choose. And then if this was an example that we did last week where if you, let's say, end up in state B, you get a reward of +5 and you move to B prime. Same thing with A. If you move to state A, you get a reward of +10 and you move to state A prime. And then if you fall off the grid, well, unfortunate for you, you end up where you were before and you get a reward of -1. Everything else is just transition, your reward is 0. So let's say when we go up, your reward here is 0 because, well, you're still on the grid and you didn't go to either A or B. And then the value of your next state, your current value is 17.5. And with a discount factor of 0.9, this is like your computed value, assuming that you're going up. So this is action go up. So keeping this in mind, we have a value of 14. And now let's say we go right. In this case, we're going right. Because we fall off the wall, we end up in the same state, and we get a reward of -1. So that's your reward, -1, plus your discount factor multiplied by the value of your next state. So in this case, which is just 16. So we have 14 and 13.4 so far. Now let's do, we're going down. your reward is 0 again. And what's the value of the next state that we're in? Yeah, 14.4. So once we calculate that, we get a value, we get the summation of 13. So we have 14, 13.4, wait, yeah, 14, 13.4, and 13. And now let's calculate if you go right. Or sorry, not go right, go left. I don't have my rights and lefts right. So if we go left, reward 0, we end up in the state next to it, and the value is 17.8. So once you add all those up, you get a value of 16. In this case, which is the best action to take? Yeah, we go left. And that's exactly what your optimal policy is in this state. You just choose to go left. And then once you do this for all of the states, this is your optimal policy. It looks a little bit confusing, but one thing to note is that if you go to state A and B, which is like corresponds to these over here, it really doesn't matter because you just jump to another state. So that's why these are kind of like arbitrary, go in any direction. But all of the other ones, these are the best actions to take. This is your optimal policy. Yep.
So you have the like 4 arrows for
Yep.
A and B, right? Is that the policy after it's moved, or is it just
In this state,
in
all of
that
the,
state?
yep, everything here in these squares is for that state.
Right.
So let's say if you recall, let's just your policy, your pi s, assuming that is your state, your pi s would just be to go left. If you're in this state right here, your pi s would be to go up, or you could go left. Yep.
So this pi star is basically only dependent on v star.
Yes, and this,
Because
yep.
I'm not sure what was the calculation that we were doing.
Mhm.
To be honest, I kind of was lost there. But
That's okay.
looking at the numbers here is basically just comparing which next states we should go to, which
Yeah.
is better for us. Okay.
Yeah, and then these next states, these values are they're the expected return for also future rewards. So therefore, you're looking at the future reward that you can get from these next states. Yep. Question in the back?
The way you set up the reward system is quite interesting because they give the formula the exact same reward per step, right? Going towards A reward B.
Sorry?
So I'm
Yeah.
worried for like from like the way where B drop, that you
Yeah.
go to the B value first 3 months. Versus shouldn't one of them like outweigh the other one? Or do they give the same reward going to both of them?
See, the reason why like are you saying like for these or something?
Yeah. Why does it
Yeah, so if you look at our state values actually, in either direction, they're the same. They're both, if you go from here, 17.8 and also 17.8. And our reward is the same as well, so it's 0. So in this case, they both have equal, the values are both equal, so therefore they'll both be kind of the argmax, which means like no matter which direction you go, you're in the best possible policy. Yep. Yeah. Sorry.
how the code or the machine decide which direction to take that if both are equally?
Yeah, so in this case, you can remember how like you can think of your policy as a distribution. So like if it's stochastic, which means like it has a distribution, you can just set like how do I explain this? You can just set a probability for each of these actions and let the computer choose one randomly based on these probabilities, if that makes sense. So it's like in this, yeah. So like in this case, it's kind of like tossing a coin, 50-50.
So what if there are 3 angles that it will be 1/3?
Yeah, 1/3. If there's 3 choices, then it would be 1/3. In this case, because there's 4. Oh, whoops! In this case, because there's 4, 1/4. Yeah. So one thing that you can actually realize is that these two Even though one looks much more complicated than the other, they're really the same thing. Why is that? So this top one is if you're using your state value functions. This bottom one is if you're just using your state action value function. If you take a look, let's take a look at, I can't English today. Let's take a look back at this diagram that we had earlier. So, if we're starting with the state, your policy, you want to choose the best possible action. If you're using your value function, you have to consider, assuming that you took this action, everything else after. So if you remember from our diagrams earlier, these actions also split up into further states. So that's what you would have to calculate if you were using your value function. But since if you're using your state action value functions, well, you're not here, you're straight up here. So all you have to do now is just iterate through over all of your actions. So that's why it looks so much simpler, but really these two are the exact same things. So this is a really nice relation of how your values relate to, or your state values relate to your state action values. And then it can be summarized quickly with this little tree. All right. Are there any questions? All right. So we're going to go into dynamic programming methods now. So all of that was kind of how do we find our optimal policy? How do we find our optimal value functions given that we have an optimal policy, or the other way around, vice versa? And this is actually what we're going to be doing, the main focus. So if you remember from last week, our incremental sample averages. So it's you're using your previously computed values to calculate a new value. Hello. So again, you're using your old estimate to calculate a new estimate, plus some other math. Step size is how much you want to change your value by, and then this right here, target minus old estimate, is just specific to this. In some other machine learning cases, this could be your gradient if you're doing gradient descent and such. But it's just this idea of using your old values to compute your new values that we're going to be continue using today. So the first thing that we're going to do is policy evaluation. So if you have a policy, you want to be able to find the optimal one, but we want to figure out how good our current policy is. And from that, if we already have a policy, we can compute our state value functions using it. So let's say if we just have a uniform random policy, we're going to go through a little bit of it, but then you can use this policy to compute values. So assuming that you're following a uniform random policy for all states, these are the values that you're going to get at the end, and we're going to go through of how to do that. Is there a question in the chat? Oh no, that was from before. Yep.
Is the graph on the left the rewards kind of?
This is your state values for each state. Oh yeah, so this left one is this is our environment of, remember how if we go to A we get plus 10 and such. This is the exact same environment.
So is it reward or environment?
Your environment will give you the reward.
Oh, okay.
Yep. So they're highly related. So the reason why we're doing this is our policy might be bad at first. If you're in every single state, you don't really want to just randomly choose an action every single time. So we want to do this idea of control, which is approximating an optimal policy. And through this, we want to we want to be able to improve our policies. So in this case, let's say, if you remember our definition of optimal or like better policies, policy or pi2 is better than pi1 because all its values for all states are better than or equal to pi1. And then we can keep doing that and keep doing it and keep doing it, and hopefully at the end you get the optimal policy. So this kind of brings us to iterative policy evaluation. The entire idea is you're using you have a policy and you're calculating its value function. You're calculating the values for each state. And you're using the Bellman expectation equation as an update rule for this to calculate this value function. So when you're given a policy, you just continuously apply this update rule and for many iterations. So basically for all states, you update your new value based on your old values. Sorry, one second. It will be more clear when we do a walkthrough example of this. But if you so you do this for many iterations, and eventually you'll reach the values for this policy. So let's say maybe at your first iteration, this is what your values look like. And V1 you then use to calculate V2. Which could look different. It looks a little bit smoother maybe. And then you use that to calculate V3. And you keep going, V4, until once you're satisfied, you have your estimated value function for your policy pi. And the entire time your policy is constant. You're always assuming that you're using the same policy. So let's go over an example of this. We're in a new grid world, and these gray squares are your terminal states. Until you reach there, you get a reward of -1 per time step. And this is an episodic task, so let's assume our discount factor is 1. And again, your actions are north, south, east, west. If you fall off the grid, you just end up in the same spot. And let's start with a uniform random policy. So if you're in a state, 50%, or not 50, 25% chance of going in either of the 4 directions. So let's do this step by step. Let's start with this blue state right here. And let's say we're choosing going left. In this case, while iterating, the probability of going left is 0.25. You always end up in this state, in this red state over here, so this doesn't really matter. Reward -1 because you had to move, and then your value currently, we just initialized everything to 0. So that's the calculations for when you're going left. Now if we go down, it's actually the same thing. Same thing if we're going right and going up. So when we calculate all of that, we get a value of -1. And this -1 becomes your value of that state after 1 iteration. And now we rinse and repeat for all the other iterations as well. And when you're calculating the rest of the iterations, you just use your previous values. You don't use the new ones that you calculated. Yeah, so if we do that for the next state, we also get -1. And once we fill everything in, everything's just -1, except for your terminal states, because once you reach there, you can't go anywhere else. Yep, question?
Like, I know why the next state changes to -1 when it goes left.
Yep.
The immediate return is -1.
Yep.
And the value of the state is now -1. So wouldn't it be 0.25?
when we're, yeah, so when we're calculating these, we use our previous values. We don't use the new one that we calculated. This is for our next iteration. This is for the things in the future that we're going to calculate. All we're using is this grid of zeros right here. Yeah. So once we have, oh, the color is not very clear, but yeah. So once we have this grid, this becomes our values that we're going to compute for the next iteration. So if we do this again, if we start in this state, we're just doing the exact same thing, but instead of values of 0, we are using the values that we got previously. We're using these values now. We're no longer using our 0 values. So once we calculate that, our new value for this state, for this box state right here, is negative 1.75. And then this state over here is negative 2. And the reason being is because, like, well, for the top state, we have a value, one of the next state values is 0. But then for our negative 2, everything, no matter where we go, the reward is negative 1, or the value is negative 1. So if we do this for all of these states, these are the values that we get after our second iteration. And then we do it again. And then we do it again, maybe 10 times. And once we do this to infinity, we eventually converge to this, to these values over here. So assuming you're following a random policy for all states, these are the values that you get at the end. So this actually brings us to our notebook. So, oh yeah, question?
This question, where did it, like in the very first iteration, I know there's like a 0.25% chance,
Yep.
sorry, 25% chance of moving into either,
Yep.
either, but where did you get the like negative 1 from? Is each action,
Unless if you're in a terminal state, each move that you do, you get a reward of negative 1. This is just how the environment is set up.
oh, okay,
Yeah.
for this specific.
For this specific environment. Yeah. Yeah.
So after the final final iteration that they have, basically based on that.
Keep going, sorry.
Oh, okay. Based on that, we can change our policy, right? That's gonna be the next step.
Yeah, so that's also like getting a little bit ahead. So once you do this, the next thing to do is to update your policy based on these values. Yeah, and that's like the eventual goal that we're going to be doing. But first, we got to figure out how good our current policy is.
Oh.
Yeah. So we're going to introduce a new grid actually. Same thing. If you gray state is your terminal state, and you get a reward of negative 1 in every step. But if you go into a blue state, you get a reward of negative 10. So it's a little bit different. And let's say we start with a random policy. So previously I shared in the Discord server in the channel, I shared a notebook, and let me just open this. So if you look in the Discord channel, there's a notebook that I shared. And then what you can do, once everyone has opened it, is that you can go to File, and then you can go to Save a Copy in Drive. All right. Yeah, so I'll let you guys set that up while I kind of explain the thing that we're going to be doing. So we're going to be, this is kind of like the pseudocode of how policy evaluation works. So again, we're determining how good our current policy is. So first things first, you have a policy that you need to evaluate, and then every single iteration, you keep track of how much your values change by, and if they change by a small enough amount, then you're good. You can say that your policy or your value is converged and you move on. But essentially what's happening, like over here, for all of the states, you calculate the next value using the Bellman equation. And with this, something to note is that you need to know the environment dynamics, because you need to know how your transitions work. So does everyone have the notebook set up? Are there questions in the chat? Thanks. Yep. Okay, so we had to create a custom environment for this, so that's what this cloning is doing. So if you just run these as well, just to kind of, I'll let those run in the background. And then how we set this up is that we numbered all of the states just so that it's a little bit more clear, and this is how the states are numbered. And then something that we did is that if you decide to go in a direction, it is possible that your environment just goes in a completely different direction. So if you're in state 11 and you want to, let's say if you want to go east, so if you want to go off the grid for some reason, the probability of ending up in the state you intended is 85% and 5% for all of these for every other state. So this is kind of like your environment may work against you a little bit. It's just a little bit of that. And yeah, so this is a little bit background information about our policy evaluation. You can read through that a little bit. And these right here are setting up your policy, your initial policy, and also your environment. So first things first, we have a random policy or a uniform random policy. So for all your states, every probability of choosing any action is 0.25. And then here we can kind of see the environment or reward distribution for all of these states. And we can use env.transitions. This is a function that you can use. So the first thing that you pass in is your state, and the second thing that you pass in is your action. And what you get is an array. It's a nested array. So each array would be for each probability of or each of the next state or reward of tuples. And the first one would be the next state that you end up in. The second element is your reward. And the last element is the probability of seeing this next state and reward. So if you remember our equations from earlier, this would be P S prime R given SA. So again, you pass in your states and you pass in your action to get this. So we already have the policy evaluation set up for you. What you need to do is write the Bellman update. So this line right here. So I'm gonna give everyone, let's say maybe 5 minutes to try this on your own, and then we'll go through it together.
Okay, cool. So what we're gonna use here is we're gonna use a function called enumerate. How many of you have seen the function enumerate before? Okay, so a couple of people. So basically what enumerate does, it's very similar to, so I'm just, a for loop. where, let me just try to spell that correctly, where essentially you, on top of just having a thing that just like counts up, you also like just goes through like all the things within what's contained in enumerate. So in this case, if we do enumerate on policy state, we're going to go through all the different items within policy state and put them into action probability. But on top of that, we're also going to be counting the index. So it's like a nice way of doing a for loop with just counting an index and also just going through everything within it. So all the index information will be captured within action index, and all the actual things within policy state will be captured within action probability. So next line is, do you want to do the rest?
Wait, can you?
Yeah, sure. Sure, I'm just gonna copy this down. So the next thing we're just gonna do is just get out the transitions. So the transitions we're just taking directly from the environment itself. So the way with it, we're just kind of like indexing that is just with the state and the action index. There we go. Oh, okay. I think one of your keys is broken. And then the next thing is, so now we want to look at all the transitions within that transition. So for transition and transitions, so I'm just gonna state. So I'm just gonna do some typing, and then I'll do some explanation in a bit. Sorry, I was trying to type it
And
up.
like, if you remember from before, transitions, it gives you an array, and each of these are, each element is another array, and of this subarray, or not subarray, nested array. Your first one is the next state that you go to. Your second element is a reward. And your last element is the probability of seeing this next state and reward. Yeah. So essentially, if you remember our, yes, I'm so sorry, thank you. If you remember our Bellman equation, the first thing that we did was iterate through our actions. The second thing that we did was iterate through our next state and rewards. And using that, we have our reward plus our gamma, and then plus our value of the next state. And after iterating through all of these summations, so we keep a running total. And then after, after iterating through all of these, that's our final value for this state. It is a little bit confusing at first, so I do recommend like afterwards looking over the code yourself, or like trying to go through it further in detail. Again, you can also like ask questions in the Discord if you have any. Yeah, this is a little bit confusing, so don't worry. This took me a long time to wrap my head around as well. You have a question?
So are we like basically going over each policy?
Yeah, so each element in this policy is your distribution of like how you're choosing your action in that state. So, sorry. You have, in your policy, there are 16 elements, and these 16 elements are all like arrays and such. Yeah, so each of these 16 represents how you're choosing an action in one state.
And you're saying that like the 4 elements within each or like just like east, west.
Yeah. So yeah, I probably should have made this a little bit more clear at the start. Each each number 0, 1, 2, 3 represents a different action. So that is north, east, southwest, I believe. Yep, northeast, southwest. And then this is like if you're in state 0, currently your probability of like these actions or your policy is just choose randomly. So you have 25% chance of going to choosing any of the actions. Yep. For time, we're going to keep going. We're going to keep moving on, but yeah, feel free to look over the code later. Message any of us if you have any questions. So the next thing that we're going to look at is policy iteration. So if you remember, what we just did is we have a policy and we're trying to figure out how good that policy is. So we calculated our state values, state value function, assuming we're following this policy pi. So the next thing that we're going to do is improve our policy. Now that we calculated our values, we got to improve it now. We got to make a new policy that's even better than our old one. And if you remember from our optimal policy formula, we just take the best action. We take the action that gives you the best value. And so this is assuming that you do have the optimal value function as well, state value function, but we can actually just apply this. Instead of using our optimal, we can just use the one that we have right now. We can just act greedily using the action that we have right now, or using the values that we have right now. So our new policy, when we're updating when we're updating how we choose our actions, we just use the current values that we have. And this new policy is guaranteed to be a strict improvement unless if your old policy was already optimal, and by that point you could just your policy is optimal, you don't need to change it anymore. And we're doing all of this to find an optimal policy. So remember how these were our values for this state or this environment, assuming we have a uniform random policy. We can use these values to choose an optimal action, optimal actions. So let's say if we're in 20, if we're in this state -20, there's a negative over here. It's a little bit hard to see. No matter if you go left or if you go up, they both. Oh wait, is that left? Wait, hold on a second. I don't have my angle. That was left. No, but if you go right or if you go up, you get your values is going to be -18. So that's kind of why our best action is either going right or going up. And then if we look at these states, these -14 states over here, your best action to go from there is to just go to your terminal states based on the value function or the values of these states that we have right now. So, like, we have this theorem, basically, you can always obtain a strictly better policy if you act greedily with respect to the value function of your current policy, unless the current policy is already optimal. So this is kind of like a summary of what we just did. And this comes to the pattern that we were talking about earlier. So it's this constant pattern of evaluating your current policy and then choosing updating this policy to acting greedily according to the new values that you just computed. And using these new values, you can, or using this new policy that you have, you can now recompute your values, and using these new values you have, you can update your policy. So it's like this cycle of evaluation and improvement. Yeah, so for policy iteration, the overarching idea is you initialize a random policy or just any policy. You first evaluate it, and then you improve it. You improve it greedily with respect to your value function that you just computed. And you keep doing this over and over again until you find an optimal policy. Yeah.
What does greedily?
Greedily just means you're choosing the best action that gives you the best immediate reward, or like remember how we were calculating like this summation over here? In this case, we're choosing the best action that gives you the highest value of these summations, which is also like your Q function in that. Yeah. So when we say act greedily, that just means you're just greedy, you want the best thing, you want the highest number possible. Yeah. So like you're starting with a value function, you're starting with a policy, you update your value function, you come down, update your policy, act greedily, update your value function, update your policy, and eventually you will converge to an optimal. So let's say if we're back in the square maze, where blue states are -10 reward, everything else is -1 until you reach the terminal state. And now let's say you're always going to end up in the state that you intend. And discount factor gamma equals 1. So based off this, when you evaluate with a random policy at first, these are, this might be a little bit hard to see, but these are all negative values. These are, this is a value function for your first policy evaluation. And then based off this, factoring in your reward and risks and such as well, these arrows are the optimal, are your greedy actions with respect to this value function that you have right now. So you first evaluate, and then you improve. Now this, it doesn't look that good still. Like, if we look back at our grid, probably the optimal path would just go along the white squares, right? But these arrows tell a different story, and that's because, well, we're just doing one iteration right now. It's okay. We're just doing one iteration right now, and we got to keep doing this until we get to an optimal policy. So, like after a little bit of time, since we have these actions now, this is our new policy that we're going to evaluate on. And after we did the evaluation, these are the new values that we get. Yep, question?
Yeah, I have a question. So when we're doing policy iteration, are the updated new policies, are they always going to be deterministic? Because that's what seems to be the case for this framework.
Yeah, so when we say act greedily, that usually just means you just pick the best one, which means act deterministically. Yep. And so based off this deterministic policy, question?
For the case where you have two equal values,
Yeah.
then you just act stochastically.
Yeah, stochastic, yep. So like 50-50. Yep, exactly. But in this case, it just so happened everything's deterministic. So we're going to, now using this policy, we computed our new we computed our new state values. And now we improve it again. And we keep doing that. And we keep doing that. So evaluation and then improvement. Using this now policy, we compute new values. And we're getting closer. So like if you do it enough times, you'll eventually reach the optimal policy and the optimal value function. So again, you have a policy, evaluate it, use this evaluation to update your new policy, evaluate again, update, evaluate, update. And that's, now that you see after we've done it enough times, we have the optimal path, which is avoiding the blue states. Yeah.
Okay, good. Yeah. So are these the state values at this point?
Yeah, so these are our state values. Something that you might notice is that in these blue states, the state values are less.
Yeah, that's what I wanted to say. Why don't we just go up?
One thing that you need to make a note of, don't forget about the reward. Because remember when we're doing these calculations, let me just go back a little bit. Sorry for the... When we're doing these calculations, don't forget about the reward.
Okay.
The reward, if you go into a blue state, is -10. So no matter how, so even though this is -2, you have to add a -10, which gives you -12.
Wait, but did we consider that in the calculations to get to this level?
No, these are just, so your reward is separate from your state values. They're two different things. You do consider it when you're, you consider it when you're calculating it for here,
Yes.
but you don't, when you're in a state, it's your expected return, assuming you start in this state and go until terminal state, assuming you follow the best policy. So assuming that we start in this state, we didn't have to transition to this state. So we don't the -10 isn't factored in here. So like your optimal policy would just to be go up twice, which is -1, -1. Yeah. Let me just check online. Yep, okay, it seems like questions have answered. Yeah, so if you see how like this is something extra that you can do is like, instead of just finding the perfect value function, finding the perfect policy the greedy policy with respect to that value function, something that you can do is just, you can relax it a little bit. You don't have to go all the way. You don't have to go all the way greedy. So instead of like acting deterministically, you can maybe act a little bit stochastically. So that's kind of what this is doing. So maybe using this, you can get there a little bit faster. This isn't really important, but it's basically showing you don't always have to go all the way to the edges. And that actually brings us to our next notebook. So we're hopefully a little bit more familiar with the environments now. So this is kind of, it looks a little bit daunting, but half of this we already seen. We've already seen 1 and 2. The only thing that's left is 3, which is your policy improvement. So to reiterate, we reevaluate our policy, we're finding a new policy based off this. We're improving our old one, and then we're going to evaluate again until we have a stable policy, which means that like it didn't change from our old one. And once we have that, we have found our optimal policy. Oh, yeah. So if you go to the notebook and scroll down. You're going to see the pseudocode for this, and then you're going to see this policy improvement. So what we're going to do now is we're going to code this argmax right here. We're going to code the updating the policy. So previously we were updating the value function. Now we're updating the policy. Yeah, so I'll give you guys maybe 2 to 3 minutes to start this on your own, and then we'll come back together. And yeah, there are a couple of, so what you need to do is implement this choose greedy action function, and you kind of have got started already, so you want to choose the best action. So you got to keep track of which is the best action so far. and use that like have to calculate the summation over here. So that's kind of like where you're starting. Actually, I'll do a little bit as well. Hurry. So can someone actually tell me, based off the pseudocode, what I'm typing next? So we have our next state reward and probability. What's the next thing that we need to do? Yep.
Multiplied by reward plus.
Yep. Yep. Yeah, perfect. So like we need to keep track of the summation so far that we have. So that's like what this this variable value is doing. So yeah, so the next thing that we need to do is exactly this formula over here. So we have a probability, and we're multiplying it by our reward plus our gamma. Oh, nope, that's not how you spell. Multiplied by the state value of our next state. And we get that using our value function. Value func. Next state. And now that we have this value. Well, we have to check if it's the best value that we have. We have to check if this action right here is the best possible one that we have. So if we're keeping track of our best value, if the new computed value is better, we gotta update our parameters. Our best action is now our current action. Oh my god. Okay. Our best action is now our current action, and our best value is our current value that we just computed. And based off this, we have our best action, and now we can update our policy. So remember, we want to act greedily. When we're acting greedily, we just want what's called a one-hot encoding, where essentially one value is zero, one element is 1, and then the other elements are just all 0. So this is kind of like a shortcut to it. So let's say if I'm going to do list comprehension. If our index I is equal to our best action, else 0. So this is kind of like an if statement, and we're iterating for over our action space. Oh, wait. Oh, yeah, sorry. Thank you. Yep. Oh, there's something goofy here. So what you need to do is wrap this inside an integer. Wrap this next state inside an integer. It's a little bit goofy, sorry. I thought I fixed that. So now that we have our policy, after you can see now our policy is just is greedy. And let's actually visualize this. So if we run all of these next ones, we have, so this one right here, we set up our policy iteration where we're first evaluating our current policy and then we improve it. And then we do that until we find our optimal policy. So once we do this enough times, at the end, you can see that we get our optimal policy. And then something that you can also do is that if you run this last one right here, you can visualize our values. Yeah, so one thing that you can do then is if you look over here, we have our gamma, we have our theta. Theta, in this case, if you recall from our pseudocode, is this small value where we determine how close we want our approximation of our value function to our policy to be. You can play around with these hyperparameters. So let's see what happens when I make gamma equal 1, when I make our, when I want to count our future rewards. Oh, I don't need to run these again. I just need to run this. Something happens here. Our optimal policy is actually to go up. And a reason why is because if you recall from how we set up this environment, is that we set it up so that it is possible to go to a different state than the one that you intended. And because of this, the calculations actually factor all of that in. It factors that in when you're doing your policy. And based off that, it thinks that the best action is to go up because you also have a probability of going in the other directions as well. Oh, nope. And you can kind of see that from this because of the little bit of randomness, the little bit of stochasticity. You actually thinks that going up is a little bit better. So that kind of shows how important hyperparameters are to when you're doing reinforcement learning, when you're tuning your environments. So like what a lot of times people will do is we will do a grid search of these hyperparameters and then pick the best ones. So this is just kind of like a prelude to how that goes. I'm actually going to I'm going to skip over value iteration because it's we're running out of time and it's very similar to the policy improvement that we've done, but instead of like going through, this is policy improvement, instead of going through all of the improvements and all of the evaluation, we're just kind of concatenating that into one loop for each, and that's kind of summarized in this right here. Yeah, so that was kind of a quick overview of value iteration. Yeah, so instead of like those two giant loops, we kind of just made it into a small, like one step. And then you just output your deterministic policy. Yeah. Next thing that we're going to do is Monte Carlo methods. So one issue that dynamic programming has, so what we just did we actually need to know everything about the environment. We need to know how the transitions are. As you recall, we used a function environment.transitions to be able to determine what our next state and what like our reward distribution is. But you might not know that. You might not know this probability. And like say, in this case, like knowing the weather in one part of Canada doesn't mean that if you go down, if you go south, it's going to be continuous. You don't know the distribution of your environment. And if you remember from Karen Bandits, what we were doing is that if in an environment that we don't know, we take the empirical sample. We take our experimental sample of average, and we're doing that many times. So there, like in this case, we have an estimate of how good this arm is, just from experimenting ourselves. And that's kind of what Monte Carlo is getting at. So instead of, in Karen Bandits, when we were just choosing an arm, in this case, imagine this arm is a state, and we want to tell how good that state is. So therefore, what we're going to do is that we're just going to take many samples of like rollouts of rewards from that state to determine our value, or like our action value as well. So Monte Carlo methods, when you're given rollouts of samples, so when you're given trajectories of episodes, state, action, reward, until terminal, you're learning the values or a policy by averaging over a large number of random samples. And you're learning from complete episodes this time. So prior to that, we're just kind of looking at the states, the next states. Now we need to actually look at the entire episode until we hit a terminal state or until we decide to stop. And with this, we don't need to make any assumptions about our environment. Oh, shoot. Whoops. Yeah, we don't need to make any assumptions about environment. We don't need to know how the transitions to the next state are. We don't need to really know what our next state is. We're just looking at, if we're in the state, what's the best, what's our estimate of future rewards. So that brings us to Monte Carlo prediction, where average, if you have episodic tasks, if you have an episode, you can break that down into the trajectory of experience. And for each episode, all you really need to do is just count the number of times you visit a state, and then you average the returns. And by averaging returns means if you remember what returns is, it's the total reward at the end of an episode. So you use that to update of how good your state is. So recall how we're doing this new estimate equals old estimate dynamic programming style? That's exactly what we're doing. So it's so you're incrementing the number, your count of how many times I've seen the state. So if you remember for Karen Bandits, that's kind of how many times I've pulled this, how many times I've picked this a number out of this basket. And then you're updating your value based off that. So if you, it looks very similar to what we did for Karen Bandits, and that's because it is pretty similar. It is pretty much the same thing, but now we're in episodes. And this looks a little bit confusing. There are two different versions of Monte Carlo predictions. The first one is called first time Monte Carlo prediction. And essentially what happens is that you're given an episode and you're doing this increment. I'll actually go to the pseudocode to explain it a little bit better. It looks a little bit daunting, but we'll walk through it. So first things first, again, we have a policy that we want to evaluate. So that's what we start with. And then we want to find our estimations for our state value based off this policy. So if you're, you generate an episode until termination. So if you remember, episode is basically like you keep walking through the environment until you hit termination, which means like you just stop the episode or you hit a terminating state. It doesn't matter, like each episode can be a different length. You can maybe reach the terminating state earlier. I apologize for going a little bit over time. Yeah, and once you have this episode, you kind of work your way backwards. So you're kind of looking backwards. Sorry, one second. You keep track of the reward that you've seen, and that's kind of like how you're calculating your reward here. So if you remember, prior we were discounting future rewards. Now we're kind of like that's actually exactly what's happening here, even though it looks a little bit convoluted. You see you keep track of the rewards that you've seen, and then you keep discounting. Maybe afterwards, if you guys want to stick around, I'll do a little bit of math to show how this works, but let's just go with this for now. And for first time Monte Carlo prediction, you're only doing your updates to your averages if it's the first time you've seen this state. So you're calculating your return going this way, but you're checking to see if it's the first time you see a state going this way. It's a little bit confusing, it seems, but really, it's just the first time that you see a state, you add a return. Yep.
Can we do this next session? Honestly, I'm lost a little bit.
Next session? Yeah.
I feel like it's an important topic, so if we try to
Yeah.
rush through it like in 2 minutes, you'll be like.
Next session is actually, like, we're going to be building on this next session, so like we will be going over this again. Yeah, it's a little bit confusing, but the entire idea of Monte Carlo really is just you don't know the state transitions in real reinforcement learning. You don't know how your environment behaves. And based off that, you need to adjust how you're learning. And in this case, you're just sampling averages. Yep.
By saying that we don't know how the environment behaves, you need the probability of going to the next act, of taking one action.
Yeah, so you don't know. So remember how we had the transitions? You don't know your transitions.
You don't know where it's going to go.
Yep, you don't know your next state. Or let me go back to this.
So you don't know what state they are that you can reach from the current state.
Yeah, let me just go here. So if you remember our transitions, you have the probability. In this case, in policy improvement and dynamic programming, we know the distributions of our probability of like seeing this state next and this reward next. But in reality, when we're doing reinforcement learning, we don't know this probability.
But we know the first two.
We know the first two. We know which state we're in, and we know the action that we're taking. But we don't know the probability distribution for our next state. And that's kind of where Monte Carlo comes in, where we're taking our sample averages, kind of like Karen bandits. Yep.
So it's basically we're experimenting through different states and actions to build a sense of the environment.
Yep. And like just to quickly go over, we're doing this. We're like estimating our value function, and then we're going to actually do the same thing. We're going to improve our policy based on these values that we estimated.
Also, this is basically a pre-step if we're in an unknown environment,
Yeah.
like AI warehouse.
Yes, AI warehouse. We got a shout out right there. Yeah, so if you don't know your environment, your transitions are unknown, so you got to estimate them. That's the idea of Monte Carlo. And yeah, I think we're out of time. So we'll go over this next lecture as well. And we'll also go through some like various Monte Carlo, what's it called, like different algorithms as well.